Hi folks, thanks for tuning in to yet another Murphy video, this time on section 4.2, apply congruence and triangles. We know what the word congruence means, and we've used it in the past with specific geometric figures like angles and segments, and we know that that means that if two segments are congruent, for example, or two angles, then their measures are equal to each other. What we haven't done yet is talk about how that might apply to polygons, where there's a lot of sides and a lot of angles. We can probably guess how that would go. So we're going to define some terminology. On the next page, we're going to talk about a theorem. We'll apply these two things in a geometric context, and then a little bit of algebra is going to be involved too. But we're going to kind of work through these concepts and see how they could apply for us moving forward. But first, the notion of congruent polygons. Like I said, with sides and angles, we know that that would mean that if two sides of a polygon are congruent, for example, that means they have the same lengths. If I tell you that an entire shape is congruent to another entire shape, like these two triangles on the bottom here, ABC and DEF, we could probably deduce what that means. That would mean that every measure that each of these things has is congruent to its other one, or its other corresponding matching part from the left triangle. So I do say that congruent polygons have congruent corresponding sides and angles. When I say corresponding here, I don't mean the same things with transversals. I mean not like the math term corresponding, but like the normal English language word corresponding, where the sides or angles would match up. So for instance, the longest side of this triangle would correspond to the longest side of the other one. I've also seen some curricula refer to it as coinciding instead of corresponding, maybe to avoid the whole like double usage of the word issue, but I think we could figure it out when I say that corresponding or matching sides and angles have equal measure. So let me hop down to this problem before I refer to this thing, which is obviously important because of the hazard sign. But if I deduce that this is the longest side here, side DF, if these two triangles are congruent to each other, then DF would be congruent to AB. The longest side of the left one would be congruent to the longest side of the right one. Same thing with EF and BC, they'd be congruent. And then the same thing with the remaining third side. Again, this is all if these two triangles are congruent. I could also say something about the angles involved too. I could say angle D is congruent to angle A, angle C is congruent to angle E, and then angle F is congruent to angle B. And maybe these two triangles, maybe they don't look congruent because really the way I jammed this into the picture in the background is that it's like a perspective drawing, so they might not look congruent, but usually the way bridges are constructed is that yes, every side and angle is of equal measure, so of course they'd be congruent to each other. So really when I say that these two triangles are congruent, what I'm doing is I'm making a big statement about all the sides and angles. I could break that bigger statement up into 6 smaller ones, because basically what I have is the 3 angles from this triangle are congruent to the 3 angles from the other one, and then the same thing with the sides. I have 3 pairs of congruent sides and 3 pairs of congruent angles for these triangles. So then if your question was, I mean in this case I guess it's kind of obvious that one of these triangles is like a rotation of the other, but if it's less obvious what side corresponds or matches with its side from the other triangle, how do we know? How do we know what matches up? And this is where I address this whole thing right here. We know what sides or angles correspond based on the way that I make my congruent statement. So I can say, for instance, if I want to show that like ED corresponds to AC in my congruent statement, maybe that was a bad example because they're on the outside, but let's go with let's instead go with DF. I know triangle side DF is congruent to side AB. So I would make sure to order my vertices in this congruent statement for the left triangle the same way that I would with the right triangle to show that the first vertex matches with the second. Note that angle D matches with angle A, F matches with B. See, they're both the 3 arcs. And then C matches with E. This is true of the angles, and it's also true of the segments, which is to say segment FE matches with segment BC. Here's FE, it's got the two lines. BC also has the 2 lines. And especially if I don't have a diagram to go with a congruent statement, I would use the fact that I'm ordering my vertices intentionally here in order to show that I know what matches with what. So even though it might be tempting to say triangle ABC is congruent to triangle DEF because you're just rolling through it alphabetically, the order in which we choose these is actually quite important. That's not to say that this is the only way that we can make a congruent statement out of this. I could start with I can start with the right triangle over here. Not right like 90 degrees, but, this one, ABC. I could instead call it BAC if I want to. I could say triangle BAC is congruent to. And I'd have to make sure that I match the vertices order of the left triangle to the same one that I'm going to do with the other one. So B matches with F, so I'd call this triangle F. Let's see, FDE. If I'm, again, making sure that my corresponding parts are indicative of what's congruent to what. Great, that's polygon congruence. Just a fancy way of saying what pieces are congruent to what. So another thing worth mentioning in this section is something called the third angle theorem, which I may have actually referred to previously for some justification, but what it says is, if two triangles have two pairs of congruent angles, then the third pairs are also going to be congruent as well. So what that means here is that since this triangle on the left has two angles that are congruent to two angles from this triangle on the right, then that means that the third pair of angles are also going to be congruent too. So we know this. If I have two pairs of congruent angles, it implies the third. And then I talk about a minor justification here. So let's say I don't know what this is. We'll call it A, and let's say this angle right here, we'll call it B. So what I know about the two arcs is that they're congruent, and what I know about the one arcs is that they're congruent. So let's call them something. Let's call the two arc one X. Here would also be X then. And then let's call this one arc Y. So also what I know about triangles is that the sum of their interior angles is 180 degrees. So from this left triangle, I can say that A plus X plus Y equals 180 degrees. From this triangle on the right side of the screen, I can say that B plus X plus Y equals 180 degrees. So in other words, if I kind of look at the corresponding parts here, if I subtract X and Y from 180 on each side, I get that A is equal to 180 minus X minus Y, and you know what? B is also, if I do the same thing on the bottom, equal to 180 minus X minus Y. So a little bit of transitivity tells me that A is equal to B, which we probably could have deduced if we had real numbers anyway, but being able to do it with variables is making a stronger statement because it says no matter what the measures of these other two angle pairs are, the third angle pair is always going to be congruent. Great. So here's some problems on the bottom, or some questions that involve either the notion of congruence or the third angle theorem. If you want to pause and take a second and try to figure this out on your own, go for it. I would suggest it. I'm going to run through it now, though. So I say to find X. Based on this diagram, I don't know that these two triangles are congruent. Again, we should be careful of assuming things. But what I do know is that the third angles here would have to be congruent. So this angle is congruent to this one. If I want to know what this is, I could again take into consideration the fact that the sum of these three angles is going to be 180. So 80 plus 45 is 125, and then 180 minus that is 55. So this would have to be 55 degrees. And then because this 55 degrees corresponds with this 5x, we know that 5x equals 55, and then x equals 11. Easy peasy, if you know what you're doing. And then I ask, are the triangles congruent? Think about that for a second. We know now that we have three pairs of congruent angles, but what it means for these triangles to be congruent is that corresponding sides would also be congruent. In other words, these three sides of this triangle would have to be the same lengths as these three sides. And do we know that that's the case? Is it enough that these three angle pairs are congruent to conclude that the side pairs are congruent? And the answer is no, we can't actually conclude that. So as far as these two triangles being congruent, I don't know is going to have to be a satisfactory answer here. So for instance, I could just make up a triangle here where let's say its side lengths like 2, 3, 4. Don't take out a ruler on me here. But if I have a triangle with side lengths 2, 3, 4, what I could have is another triangle that's kind of a blown up version of this one. That's maybe the side lengths are twice as big. So 4, 6, 8. And it could be the case, actually it would be the case, that these angles are congruent to each other. So I can have pairs of congruent angles without having pairs of congruent sides. So just because I satisfy some of the criteria of having congruent triangles doesn't necessarily mean that the rest of the criteria is satisfied too. I can have three pairs of congruent angles without having three pairs of congruent sides. So this isn't even a hard no. It's just a we don't know. We need more information. We need to know something else about these sides to come to this conclusion. Here's some more stuff. If you want to pause it and take a minute to work through this, that'd be great. But I'm going to just keep rolling. I'll stick with blue, actually. If quadrilateral math is congruent to quadrilateral, cool. Definitely no subliminal message there. Label each remaining side and angle with its measure, and then determine if the shapes are trapezoids. Trapezoids are defined as being quadrilaterals where there is exactly one pair of opposite sides that are parallel to each other. So like these, and then not the ones that obviously if I were to extend them, they'd intersect. So basically, do I have this? I'd have to show that these two lines, or sides, are parallel to each other as well as these two. We have to do a little bit of work to get to that point. So let's try first. Let's fill in the stuff that we know. So I know that, for instance, I don't know angle A, but I know that it corresponds with angle E. I don't know angle E either. That's not great. What can I figure out? I want to know H, and I know that H corresponds with L, and we do know L. L is 69 degrees. One thing here, maybe an additional piece of information that we might need to know. I don't know if you know this already. The sum of the interior angles of a quadrilateral is 360 degrees. Actually, I do remember. We talked about how to do this at the beginning of the year, but the sum is going to be 360. So what I could do is I could take 101 plus 69 plus 79, and then find the remaining angle necessary for these to add up to 360 degrees. Let's see. Mental math. Okay, 101 plus 69 plus 79. 360 minus that. We end up with this being 111. And then if I were to fill in the remaining pieces from the other triangle, or not triangle, I do too much triangle stuff, quadrilateral rather, I get this. I also know that this top bit is 4.5, and this would have to be 4.9, and this is 5, and this is 8. This is strictly based on the fact that these two things are congruent to each other, and that I know what corresponds with what, based on the way that the congruence statement is laid out for us. So all the measures are going to be the same. We just have to find out what matches with what, because the sides and angles are similar enough to where it's not incredibly obvious. And I know I should have degree marks everywhere. So then the question is, are the lines parallel to each other? Well, if we go back one chapter and think about transversal stuff, what I should be looking for, I know I could do it with vertical angles, and there's other ways to do this, but I think the most obvious way is to ask ourselves, are these two angles, which are consecutive interior, are they supplementary? And the answer is no. Almost, but no. 101 plus 69 is 170, which is not a sum of 180. Same thing here. 111 plus 79 is 190, which is not quite the same thing as 180. So the answer is no here, because of the consecutive interior angle theorem's converse. We don't have supplementary angles, so we don't have parallel lines. Bummer. With the problem on the bottom, let's see. I'm just going to roll through this. I'm going to assume that you figured it out already. If I start just answering things using a combination of like vertical angles and the fact that the sum of triangles' interior angles is 360 degrees, I'll do some linear pair stuff here. I'll get these. This is 60. Let's see, what else? So these two are congruent to each other, so this is 45. So 60 and 45 is 105, which means this has to be 75. And then this guy, angle CDE, plus this 30 plus the 75 make up a straight angle. So they'd have to be 180 degrees. So this is 75 also. And then that should cover all of these. So let's see. BDN is this one here. BDN is 75 degrees. ANB is this exterior angle on the outside. That's 120 degrees we just found. I know I'm doing this rather quickly, but it's a video, so you can go back and rewind if you want. This is also 75 degrees. Great. Again, most of what I did here was just using the sum is 180, linear pairs are 180, vertical angles are congruent, that sort of thing. Easy, nothing we haven't done before. Here is something, though, that may vary based on your middle school experiences. If I want to solve for x and y here, and pay attention because there's actually a homework question very similar to this. I'm going to throw a big star in the middle of the screen so that if someone's like going through this quickly, they know. This is important. Make sure this is a skill you get down because this is strictly Algebra 1. What we should note here is that there's two variables, and I can set up a couple equations involved with them. So like I could do the whole sum is 180 thing here. This is 158 degrees, so this would have to be 22 degrees. And since these two correspond, I can say 4x plus y equals 222. And the problem's not quite easy enough to actually solve here for x and y. Oh, I'm not restarting. Sorry about that. Sorry about that noise. But 4x plus y equals 22 isn't enough information to solve for x and y individually, because if I have two variables, I need at least two equations in order to find the numerical value of 1. So I need a second equation. Fortunately, we have another expression involving x and y here. I can do some third angle theorem stuff and say that this 28-degree angle is going to have to be congruent to this one up here. And I can conclude that 6x minus y equals 28. So now, I don't know how you would handle this. This is called a system of equations. It's when I have two equations for two variables, and I need to find some way to combine these pieces of information to solve for x and y. This is the thing when you were in middle school, though, you learned 3 ways to do this, I imagine. You learned graphing. I could solve for y in each of these and then graph it. I could do substitution, which is to say if I solve for y in one or the other, I can plug that quantity in for the other one. So for instance, if I solve for the blue y down here and the magenta y up top, I can set those y's equal to each other via transitivity, and then I'm left with only x stuff. Another way to do this, the way that I'm going to roll with right now, is the notion of elimination, which is to say, if I combine the left sides of these equations and I combine the right sides of these equations, if I just add the corresponding pieces, then 4x plus 6x is 10x, and positive y and negative y is 0y, so nothing there, and then 22 and 28 is 50 when you combine them. So I'm left with 10x equals 50, which gives me x equals 5. That method's called elimination because these equations, the textbook author here is nice, they made the equations such that when I combine the corresponding pieces by adding the left and right sides together, the y's eliminate, thus elimination. And when they eliminate, that leaves me with only the x's. Now I have a one-variable equation, which means I can solve for it. In terms of finding the y, though, take this x, put it somewhere. Top one's kind of easy, right? I get 4 times 5 plus y equals 22. So that's 20. So 20 plus what equals 22? The answer is 2. So 5 and 2 are the answers to this problem. I imagine the other one, I forget what number this is in the textbook, but the one that comes immediately after it is a very similar problem that involves solving for a system of equations by making two equations and then doing this sort of thing. You should be prepared for this now. I imagine it's not going to differ that much. One more thing that I want to talk about before the conclusion of this video is your favorite thing, going into the notion of proofs. How do we prove two triangles congruent? The good news is, in this video, we're going to do it a way that's way, way longer than you're ever going to have to, because in sections 4.3 to 4.5, we actually learn shortcuts that kind of expedite this process. But if we're just going to straight up evoke the definition of polygon congruence or triangle congruence, that means we need to show 6 things. We need to show, remember what we did back here. Being congruent between these two triangles meant that we had 3 pairs of congruent angles, 3 pairs of congruent sides. So that's 6 things altogether. I'd have to show 6 things here. One of which is brand new, so I made a note of it. It's not new, actually. If you remember the thing for it, then, like, you're awesome. But we haven't actually used it yet. But anyway, let's proceed forward. If I want to show that there's 6 pairs of congruent angles and 6 pairs of congruent sides, we'd probably have to keep track of that in some way, because that's a lot of stuff and it's easy to get lost. So my suggestion to you is to label each pair of sides as an S, and label each pair of congruent angles as an A. You'll see what I mean once we get started, but let's start with the obvious stuff. We're straight up given that A is congruent to D, right here. That's one thing out of 6 down. Another thing is that we're told that these angles are right. That's what the diagram tells us. It's a very small step to say that if they're both right, then they're congruent. That's called the right angle congruence theorem. That says all right angles are congruent to each other. So we get ABC is congruent to BCD. Remember, there's other ways to call these angles. But I can't call this angle B, remember that, because B is also the vertex of this guy, CBD. But anyway, that's 2 A's. If I have 2 A's, I can always get the third one by using our new friend, the third angle theorem. So I know that ACB is congruent to CBD because of the third angle theorem. If we got those 2 A's, we can guarantee the third. Voice crack. Feel free to make fun of me later. As far as sides go, we got one of those given to us. AC is congruent to BD. That's an S. It's not explicitly given to us that AB is congruent to CD. Close, though. We're given that they're both 8. And then, again, it's a very small step to say that if they're both 8, then they're equal to each other. Their measures are equal, rather. And if their measures are equal, then the shapes themselves are congruent. So let's do the 2 marks there and there. And then what else? Because we're one thing away. We're one thing away. We can see what everything else matches up with. We know that AB matches up with CD. AC matches up with BD, but then what about BC? What does that match up with? And what you should be thinking to yourself is that it's in both triangles. It's shared between both triangles, so really it matches up with itself. I don't even know why the bells are going off today. So if something matches up with itself, if we want to note that BC is congruent to BC, do you remember the thing that says any shape or any segment is congruent to itself? If you do, then you know that it's the reflexive property. That's a big deal. The reflexive property is going to show up in proofs like this whenever basically there's some shared segment or angle between the two, usually triangles, that we're going to try to show congruent. So be very aware of shared things implying the reflexive property is going to be used. And also know that in the future, once we do our shortcuts, if I ask you to do a proof, it's going to be about half as long as this. But anyway, at this point, we got the 3 angle pairs, we got the 3 side pairs. We can wrap it up and say ABC is congruent to DCB, because that's what it means for polygons to be congruent. So if you stuck with it this far, then thanks. Recognize that it will get easier and a little more fun in the future too. So right now, thank you for watching.